year or so, I've been working on a programming language called Lucent. So let's get right into it. So the structure of this talk, I'm going to first talk about Lucent, and then I'm going to give a demo of what I have so far. I was planning on doing some compiler theory, but seeing it's probably not enough time, I might leave that for a future talk. And then finally, I plan to talk about how Rust has helped me with programming Lucent and some other things you might want to know about when using Rust. As always, if you want to ask any questions, just feel free to do so, raise your hand or whatever. So yeah. Cool. So to start off, I want to talk about how a typical program compiles on your computer, right? And this build process that I've shown up on the screen here, that's for compiling a native application. So this isn't something like JavaScript or Go. This isn't like JavaScript or PHP, but it is for stuff like Go, Rust, C++, C, that sort of stuff. And so what happens here is that you write your code, like say in C++, and that gets put into a source file. And then that source file goes to your compiler, who turns that source file into something called an object file. And an object file is sort of a file that contains binary instructions, but it's not quite runnable by the operating system yet, right? And particularly object files are fed to linkers, who turn object files into the final binary, right? And you can take any object files you want and feed them to the linker, as long as the linker can understand that object file, right? And there's also one final part called the linker script, and that's just a series of instructions that tell the linker how to take your object files and turn that into your final executable. Now, I say this is the typical native process, but in reality, all of these steps, the compiler, linker, and linker script, they're just abstracted away by the Rust compiler or what's running the Rust compiler. So you don't actually see the linker and linker script usually. But underneath that, that's what it looks like. And the problem with that is, let's say you're developing something for, say, an embedded system or for operating systems. You need to control how the sections that are in your object file are actually placed in memory, right? And to do that, you need to tell the linker how to put these sections into the final binary. And the way you do that is by writing a linker script. And unfortunately, linker scripts are kind of like black magic. You might look at that and think, what the hell's going on in that, right? And I know I certainly felt that way when I was trying to write a linker script for my operating system that I was writing in Rust. And to me, it just seems that you have to crawl through a lot of documentation from like GCC just to understand how to write a linker script, and it's just not a great thing to deal with. The other problem with linkers as well is that if you've ever tried writing a program in C++ with libraries, then you'll probably have come across a linker error, and you look at that and you're like, what the hell is going on in there, right? It just tells you, hey, we're maybe missing some symbol, and it might be in this function, but we can't tell you exactly why we are referencing this symbol from this function. And so link errors kind of just, they're not great either. And one problem with, and one of the reasons for this is that when your compiler turns your source code into an object file, your linker usually doesn't have access to a lot of the line numbers or debugging information that's in that object file. So it can't tell you exactly where the error is. And also, it doesn't understand the object file that's produced by your compiler. And so that's why it can't give you more information about it. And so, Lucent's solution is just get rid of the linker and the linker script entirely and just replace all of that with one single compiler. And so now you just write your Lucent source file, which contains more information, and that feeds it into Lucent, which just turns it into a binary for you. So any questions so far? Cool. So here's an example of Lucent source code. So one functionality of the linker script is that you can tell the linker exactly what address to put some sort of executable code, right? And so you hear about how programs are loaded by the operating system into memory. And maybe you don't have a great idea of how exactly it does that. But when your program, when your linker produces an executable, it has a bunch of sections in it, and along with each section is some metadata that tells the operating system, hey, I want to put say the hello world function at address maybe 1000, or maybe I want to put this other function or static variable at address 2000. And that's how it does it. It puts the metadata in the final binary, right? And you usually do that with a linker script. But here, you can put the address directly in your source code. So you can tell Lucent, hey, I want to put this entire module under the address at 1 million, right? And the other important thing is that since you're not having a linker step, you have all the information available to you when you compile the code. So you can actually introspect the addresses of symbols at compile time. And in C++, you can do this as well. What that involves is that the C++ compiler will produce an object file that contains holes in it, and the holes tell the linker, hey, replace this hole with the address at some maybe specific symbol. But you can't do a lot of complex computation with that. You can't say, hey, let's do this hole plus some sort of offset. So having everything inside of a single compiler makes this really easy. And so, as a question to the audience, does anyone know what header this represents? The hint I can give is that it relates to operating systems. Maybe I can give another hint, it relates to bootloaders. All right, fair enough. This header actually comes from the multi-boot bootloader. And so if you've ever tried using Linux, I believe Linux uses grub, and grub supports multi-boot. So if you use this header in your operating system kernel, you can load your operating system with grub or any other multi-boot supported bootloader. That was just an interesting fact. So one other thing that Lucent provides is inline assembly. If you tried writing inline assembly in C++ or Rust, it can be quite daunting because every instruction has to contain information like what variables am I going to modify, what registers am I going to modify, how am I going to modify them, like is this variable you're accessing a constant or is it like changing? And the reason it needs to do that is so that it can tell the register allocator what registers to avoid using such that it doesn't conflict with the instructions you've written in inline assembly, right? And the way Lucent bypasses that is when you use a register in Lucent, the register allocator from Lucent will just never use that register for that function. So you can be guaranteed that it's not going to touch your register or mess it up. One other thing that I think is pretty unique to Lucent is that you can have arbitrary compile time execution. And what that means is if you want to, say, embed a x86 instruction or some sort of assembly code, what you do is you write a function that actually returns the byte sequence for that assembly code, right? Because assembly code gets turned into binary at the end of the day. So you can just write a function that writes that binary, returns that binary, and then the inline keyword will turn that binary and place it directly at that call site. So if you want to say halt, you just do x86.halt, and then you can just inline it. And what that also means is that it's really easy to compose assembly functions as well, right? All you have to do is just concatenate, let's say x86.halt with some other instruction that you want to execute, just concatenate it, and just put it under an inline. So it just works out. Cool. As an overview of the language, it uses whitespace indentation. So maybe this one's a bit controversial to people who don't like whitespace. Maybe they've been blindsided with Python. Personally, I like it because it means that you don't often have a lot of empty lines with just a curly brace, and so it's easier to look at all of your code. You can fit more lines of code in the same space. As I've explained already, it also has arbitrary compile time execution. Not a lot of languages have this. People who've used Lisp maybe have tried compile time execution. I think it's a neat feature. I know Rust is moving towards having a lot more functionality in their const function execution, but it's not quite the stage where you can open a file with it, right? You can just do some mathematical computations or whatever. But having it be arbitrary means that you don't need a build system, because the build system is just integrated into your compiler source code, into your source code, right? If you want to build something, just have a compile time function that places it somewhere and does it for you. One other thing is that you can directly embed libraries and object files in that. So you can just say put a keyword load library.a or library.out, whatever you like. It just puts that directly inside of the final binary it produces. One last thing, it's a strict static type system. So just like Rust and less like C, but kind of also like C, everything is typed and everything is strictly typed as well. So you won't be able to just cast things implicitly. And I think that's good because it allows you to avoid having lots of errors that you might have missed. And it's also one thing that I really like about Rust, because it doesn't let you just cast things willy-nilly. Lol, no generics. I don't know how many people have used Golang here. A little bit? Okay, fair enough. Golang's kind of I've heard it's a little bit like the antithesis of Rust in some ways. Having generics means that it complicates the language a lot, and it also means there's a lot of opportunity to really bloat up your program, and it also increases compile times a lot. So this is one of the main reasons that Golang advertises their fast compilation. It's because they don't have any generics, or at least they didn't have any generics, but Go 2 is coming out soon, and apparently that's going to have generics, so maybe this meme isn't so accurate anymore.
Also, that's one of the guys behind the whole party. There's so much generics and has a nice ego.
Yeah, that's true. So, cool. Any questions?
Does it work?
Well, I'll explain later.
Okay, cool.
Yeah, so here's the roadmap. So currently, I'm actually rewriting Lucent. So I'll go through each item. Parsing works, and what parsing means is taking your source code and turning it into some sort of data structure that your compiler can understand. And usually this is an abstract syntax tree, for those that know about that. Error reporting works. I'm a big fan of Rust's error messages. They are so neat, so clean. They just tell you directly where it is, and even shows the code where the error was. So I have that as well, and so I really like it, and so yeah, that's why I have it. Bidirectional type inference. If you know what that means, you know what that means. If you don't know what that means, it's basically just you can type variables and it will infer the rest of the variables for you. So just like in Rust, you don't need to assign a type to every single variable. It will just do it for you. Incremental compilation. This means if you only change a part of the program source code, it doesn't need to compile the entire thing all over again. And that is really quite essential, especially for really big projects, because obviously you don't want to have to recompile tons of files if you just make one small change. And it also comes naturally as part of IDE support. So I also have a language server implemented, and that just basically connects to a ton of IDEs. So one of them supported is VS Code, another one is IntelliJ, and it means that you just need to have one single language server, and any IDE you use will get the features of that language server you've written. So currently I've implemented GoToDefinition, so you can click on a variable or click on a function and see where it's being defined. And I've also got syntax highlighting. And the unique thing about this is that it's compiler aided. So sometimes your syntax highlighting might not highlight, say, a module that's defined in another file. Well, this one uses information that it gets from the compiler to actually tell that actually, yes, this is a module. I'm going to highlight it and say red. So I like to call it perfect syntax highlighting because it matches exactly what the compiler sees, but up to you. Now, the thing I haven't implemented quite yet is x86 compilation, so the x86 backend. So before the rewrite, I did have x86. I did have x86 backend, but unfortunately, the x86 instruction set is kind of terrible. And so that's why I'm kind of glad that Apple has decided to start moving to ARM. So like just for reference, x86 is what is called a complex instruction set, and they have a ton of instructions in there that you have no idea where to begin with using them. They're like 20 characters long. Like, come on, who needs those? Someone needs them obviously because they put them in. And it also means like they have some really weird quirks with their instructions. For example, their divide instruction only works with the EAX register. And that means when you are emitting your instructions, you have to be careful to only put EAX when you're using a divide. And it just means you have a ton of edge cases that you have to consider as well. And so the resulting code from that I wrote in Rust was so bad that I decided to, I just need to restart. So that's why I'm rewriting the compiler. So it's not quite there yet, but I'm making progress. And one final thing is compile time execution. Haven't quite got that done yet, but I think that'll come after x86 backend. And that's going to be very comparatively easy. Currently it's at 5,300 lines of code. I like to say it's actually more than that because my code style of Rust is a lot more packed than what Rust format gives you. I actually don't like Rust format that much. I think the defaults are not great. But yeah, any questions?
Oh yeah. Well, have you thought about targeting RISC-V?
Yes, that's on my roadmap.
Oh, cool. Yeah.
I like RISC-V as well.
Yeah, because it's quite a simple instruction set.
Yes. Yeah.
Very
For
simple.
now.
For now, yeah.
Yeah, the problem is that x86 has had 30-something years of jumping part on. That's why it's such a mess these days.
Yeah.
Yes.
What do you use for parsing? Do you use the same tool?
Sorry?
Do you use something to create a parser?
I use Tree Sitter. Have you heard of it? Yeah. Tree Sitter gives you incremental parsing for free, and it also gives you error recovery for free, and it also gives you syntax highlighting for free. So I get a lot of things for free by using Tree Sitter, so I'm glad I used it. Cool. Any other questions? Okay.
Why x86 and not x86-64?
Sorry, I mean all of them.
Oh, okay.
Yeah, and x86-16, because you need to use that for writing a bootloader. Cool. So I guess I'll get onto the demo. It's probably going to be a short demo because the only thing I can really show off is my language server. But here you can see the syntax highlighting in action. It's a little bit hard to see it, to be honest. Is that a little bit easier? Okay, cool. So you can see if I remove, say, this variable there, it's going to highlight all the places where I've used line. It's going to tell me, hey, you haven't defined this yet. And if you also right-click on something, you can also go to definition. Well, that's not quite right. Yeah, there you go. It goes go to definition. It also works for functions as well. So you can go to definition for that as well. You can also define data structures in there as well, but a lot of these aren't quite implemented just yet. Mostly been focusing on the actual compilation step. But yeah, that's pretty much everything that I have so far for the language server. So any questions about this? Okay, cool. Oh, one last thing. I do want to talk a little bit about the module system that I've implemented here, because having a module system that works well with incremental compilation is surprisingly hard to get right. So what happens in Lucent is you have what are called root files, and these are where the compiler starts off from searching for functions and symbols of whatever. So here I've defined a root file called main.lc, and the IDE uses this to search within this directory and see it's got a main.lc file. And then from there, it's going to look for other files that are defined within use. And what that means is if you change a file, say like in Fibonacci.lc, it can go all the way back to the root and then do everything from there, instead of having to start from the root again and then repassing everything. So the explanation is probably not the best. I go into a bit more in compiler theory and stuff, but basically if you have a root file and you separate all your modules into separate files, it makes incremental compilation a lot easier. And you'll notice in Rust as well, in the Rust programming language, every single module that you define has to be in a separate file, like usually. You can define modules within the same file as well, but the boundary between modules is at the file level. And that makes the Rust compiler's job a lot easier, because it means that when they want to look up a symbol in a certain module, they know they have to go through certain files to get there. And so that's one of the reasons why Rust is able to have good incremental compilation. And it makes sense, right? Because especially compared to languages like C++, where you directly include a file instead of having sort of like a structured module-based system, it means that if you want to change something in there, then the C++ compiler has to go looking through all of these includes to figure out exactly what is being changed. And that's just really bad for compile times. Cool. Right, so let's talk about Rust now, because that's what we're here for. So the first main feature that I think is absolutely crucial to writing a programming language in Rust is that Rust has what is called algebraic data types. So you might know these as enums. The functional programming language world will call these an algebraic data type. It's totally up to you. Enums tend to be associated with like C++ and Java enums, and those aren't as powerful as Rust enums, so I like to call them algebraic data types. So for those that don't know, in Rust you can attach any values you want to a enum variant. So here I have a variant called block, and inside of the block variant, I've put in a type called box and then SLUnit. And you can just do whatever with each of these variants. And algebraic data types are especially useful for representing what are called abstract syntax trees. So just like a brief explanation, an abstract syntax tree represents your source code as a tree. So let's say you have some sort of expression that's like 1 plus 2. Well, 1 is going to be a node, and 2 is going to be a node. And the node that joins 1 and 2 is going to be another node called plus. And so plus joins 1 and 2, right? And that's what you repeat all the way up to your entire source file. And that's an abstract syntax tree. And if you think about it, every single node that's in your abstract syntax tree has children, and each of those children is also going to be abstract syntax trees. So you can just represent those with an enum that represents a single node, and then each variant is like each type of the node. So like you would have one for integer, you would have one for a binary operator like plus, and then you just have more nodes inside of those variants. Now the one problem with algebraic data types in Rust is that if you want to have a recursive enum, which is what we primarily have for an abstract syntax tree, you need to have some sort of indirection to the node's children, right? You can't have an infinitely sized type in Rust. Incidentally, you can have an infinitely sized type in functional languages, so they don't have this problem. And if you use something like an arc, which is an atomic reference counter, or like some sort of index to each node, then you can't pattern match on that. And that makes me really sad, because that means if you want to say you want to find all the nodes that have 1 plus 2 in them, right? So, intuitively you would be like, okay, the first thing has to be a plus, and then the left one has to be a 1, and then the right one has to be a 2. And you just put that in like a single expression, right? But unfortunately, if you have indirection, like say a box or a vector or like an arc, then you can't do that. You have to actually go into the left child and then unwrap that arc or unwrap that vector or unwrap that whatever indirection you have. And that just makes working with these sort of trees a lot more convoluted than it needs to be than other languages that support algebraic data types. If you want to add some sort of behavior to your struct, so maybe you want to make your struct hashable, like you want to put it into a hash table, or you want to make it like clonable, debuggable, or whatever really, it's easy. You just add a derive and then you're done. I use it frequently throughout the project, and I hope you guys will too as well. Yeah, go ham. It's one line. And Rust has macros as well. And it has two types of macros. One of them is a declarative macro, which is what I've shown in this screenshot here. You see queries and curly brace and then some syntax I've defined myself inside of the macro. And it also has procedural macros. And this is the stuff that Serde and other really complex libraries use. So declarative macros, they are really nice. They're versatile, so you can pretty much define almost any sort of syntax that makes sense. And it's also really easy to make. You just have a macro rules sort of block in your code, and you can just use that as your macro. And unfortunately, the macros in Rust, while they are a hell of a lot better than other languages like C, their whatever macro they have, the errors are a little bit cryptic. But in exchange for that, the macros that you define are usually corrective, right? You're not going to have some sort of missing bracket or whatever if you use one of these. And I guess one final note is that you should prefer to use a declarative macro if you can, because if you use a procedural macro, first you need to define it into a separate crate, which is, well, it's a pain. And it also takes up a lot of your compile time. And if you've ever used a library like Serde in your project, then you will know that Serde usually takes I don't know, anywhere from 5 to 20 seconds to compile. And it's a real drag on your compile time. So I suggest using a declarative macro if you can. Right, lifetimes. So lifetimes, I guess you can say it's one of the bread and butter of Rust programming. Turns out actually you don't need to explicitly define lifetimes in your code that much. If you use a reference, then you'll need a lifetime for that. But anything else, probably web programming, it's usually just handled for you. But the unfortunate side effect of that is that you probably don't gain a great understanding of lifetimes at first, because they're handled for you. And when you do need to handle them, they can often be quite cryptic, as I found out with this trait here called visitor that I had to define. So in general, my experiences with lifetimes have been trial and error. Let's put a -a in here and see what happens. and so they're not obvious. And one particular example where they weren't obvious for me is that if you have a reference to something, so maybe you have ampersand s, where s is some sort of variable, then you have a lifetime on that reference, right? Let's call it dash a. And then let's say that s itself also has a lifetime. Well, the reference lifetime dash a actually needs to outlive the one that's in s, right? And unfortunately, because it's not explicit, you don't really think about it when you're actually defining these lifetimes. And so it took me a while to realize that actually I needed to have these constraints on my visitor trait for my code to work. So there's some stuff that the Rust compiler does for you, and you really need to be aware of what it actually does for you to fully take advantage of lifetimes. One final thing, I guess, about lifetimes is that they tend to be infectious, as a writer called John Goodwin says. He also wrote the Cone programming language. And what he means by that is that if you define a lifetime on a struct, then any structs or functions that actually use that struct will have to define their own lifetimes so that they can be passed down. And so if you change one struct to have a reference or some sort of lifetime, then suddenly you might need to change thousands of other structs just because they rely on this one small struct. So when you're designing the architecture for your Rust program or project, it might pay to be aware of what sort of things will end up having lifetime so that you can take them into account early on. Any questions? Okay. So, monomorphization. That's a really big word, but it means something really simple. When you have generic types in your program, what the Rust compiler is going to do is going to make a copy for that function each time you use it with a different type, right? So this example up here, I have visitor reference to import reference visitor. So reference visitor is a trait, and you could have a number of structs that implement this trait. And for every struct type that's passed into here, it will create a copy of this function just to handle that specific struct type. So if you have like 5 structs that implement this trait, you might have 5 different versions of this function that are all specialized to that specific struct. And this is part of the reason why Rust claims to have zero cost abstractions, because at the end of the day, your generics get removed, and then what you're left is 5 different functions, all specialized to the same thing. So it's as if you never used generics in the first place. So zero cost abstractions. The unfortunate side effect of this, however, is that, well, you're duplicating the same function 5 times, and that's going to cause a huge amount of code bloat in your final binary, right? Because you've got all of these functions that do almost the same thing. They just have one little type change somewhere. So Rust makes it easy to switch between monomorphization and what are called trait objects. You might hear this being called as virtual dispatch in other languages. And you just change the keyword import to dyne. And dyne stands for dynamic here, and all it means is that instead of having 5 different functions that all do pretty much the same thing, you have a single function that takes in a parameter along with some extra information to help it figure out how to do its job. So especially if you have a function or struct that's using thousands of times by different types, and this is a big problem for libraries as well that are used prolifically. I think Serde might be one of them. Then you could have massive code bloat issues. So it's something to pay attention to.
So, sorry, I have
Yes.
a question. So, if you're building a library or you're building your own language, you're gonna aim for the dynamic one, right? Because you're gonna get a lot of exposure from the consumers, right?
Yes, that's what I would go for. Although it does depend a little bit on your library's audience, right? If you're targeting low-level stuff, then I probably wouldn't go with virtual dispatch because your clients are probably going to go for performance and optimizations instead of like dynamic dispatch. But something like a web app, I would usually go for Dyn.
But regarding the previous one, which is like the old way of doing things, I mean, the CLR from C# does the same thing. It copies the reference, like it creates the middle binary code, which is not binary code, it's like bytecode kind of style, and it creates the same thing. So it's actually creating a lot of classes. So if it's only low amounts of classes that needs to be represented with it, you're gonna be wanting the first one. But if it's a lot, then the dynamic one. Is there a way to guess how many do you have and be dynamic on where, like your usage of the implementation or the dynamic one? Can you swap them knowingly based on your abstract tree? How many copies do you have to do? If it's more than some number, you can do the other one?
I'm not aware of a method. I don't think there is.
No, we can have optimization of compiles, but I have no idea. I just.
I mean, just in general, what I'd say is if you're going to be calling that function a lot, try static, like the impl. Whereas if you're going to use a dynamic dispatch, it does take up quite a bit of performance. If you're going to be calling it a lot, if you're going to be calling it not so frequently, then it's not such efficient.
Mm-hmm.
Cool. So one more thing, package managers. Rust is really, really good at making their package managers. I know coming from C++, you might have to say if you want to use a library, you have to maybe install it with your own system package manager. Maybe you need to copy it from like GitHub or something. And then once you actually like put it, you have to mess around with CMake to actually get the library detected, or maybe you end up with some linker errors because you have incompatibilities with your library versions. It's just a nightmare with C++ to get a library installed. Like, come on, I just want to use this one library. In Rust, it is super simple. You just add a single line and you're done, usually. 99% of the time, this is what happens. Sometimes you do need to mess around a bit, but it is super duper easy to use a library in a Rust project. And one side effect of this is that it also makes it really easy for people to use libraries even when they're not needed or when there are better alternatives. And I know the JS ecosystem has a big issue with this, with, what was it, like gigabytes of node module files.
Yeah, that's partly due to how the
Yeah,
works.
it's not great. Right, yeah. Better alternatives out there now. But all the same, try to be wary of your compile times, right? You can use a lot of packages and you can also make your program compile really, really slowly. And especially with projects like Serde, and sometimes you'll find that actually two libraries within your dependencies are actually using two different versions of Serde. And so now you might have to figure out exactly which version to use so that they are compatible with each other. Or maybe you just want to like save some time by removing one version of Serde you don't need. So that's just one thing to keep in mind. And also with procedural macros, like I said before, they use a separate crate to compile your procedural macro. And almost every single procedural macro uses two libraries in the Rust ecosystem called syn and quote. And these two libraries are responsible for parsing Rust source code so that you can use it in some way to help you write the macro. And it also means that, well, you're going to have to compile syn and quote for every single procedural macro you're using if they're different versions. And So usually I try to avoid using procedural macros until it becomes a real necessity. And one last thing, your folder size tends to be quite big for building, and this is especially true if you're using a lot of dependencies, and also if you have incremental compilation, because the Rust compiler has to store more information about compiling your code so that it knows what to skip next time. So yeah. So I write Lucent using the nightly compiler, and this used to be a much bigger necessity a couple years ago because pretty much every single cool feature was in nightly. Now only a handful of them are, but I still like using nightly because there are still a number of features that I think are just really nice to have. One in particular is this feature called OneCell. So I know maybe some of you guys have heard of the lazy static crate. If you want to define a static variable in your Rust code that's initialized. Well, now you don't need to do that with this feature called OneCell. It's actually in the standard library now. So you can just use OneCell, and that does pretty much the same thing. And it has more than just static variable initializing. It also does things for like synchronization of static variables, and also like just a counter to keep to make sure that you're not initializing them more than once. So there is a lot of treasure in the nightly feature section, so just keep that in mind as well. However, if you are writing a library, the general consensus is that you should probably use stable, because some consumers will probably not want to use nightly as it's naturally not as safe as the stable compiler.
Question.
Yes.
Is the OneCell crate that you put it in Lucent library, or
Sorry, what?
is the OneCell feature the OneCell crate and then they put it into the Lucent library, or is that their own implementation?
I think it was their own implementation. Pretty sure it was.
I believe the person made it collaborative.
Yeah. It was a collaboration effort, but it is specifically part of the standard library. Yeah. Any other questions? Okay. Cool. Well, if you're interested in building your own compiler, these are the resources that I would recommend. So the first one is a book called Crafting Interpreters. It is completely free to view online. It's written by the same author of Game Programming Patterns, if you've ever read that book as well. And starts off with Java, just get your feet in, and then it moves on to using C. So you get the views of both worlds. The second resource I would recommend is a series of blog posts by Nora Sandler called Writing a C Compiler, and it just covers how to step-by-step write a C compiler using C. And this compiles to x86 assembly as well. One of the most prolific books in the programming languages community is the Dragon book. It's not actually called that, but the picture on the front cover of it is a dragon, so that's why it's called the Dragon book. And it is pretty much a big textbook on how people write programming languages today. Well, 10 years ago, maybe 20 years ago. It's a little bit outdated, but it covers a lot of interesting stuff that you want to consider for your programming language and compiler. This fourth one is a Medium post written by, I'm not going to pronounce that, but it is covering type inference for beginners. Type inference is a surprisingly diverse field, I would say, a little bit mathematical and a little bit daunting if you haven't seen some of the notation that's used for type inference. So yeah, it's really nice that someone wrote a Medium post about it, so that we can understand it without having to go through a 4-year university course on types and stuff. The second to last one is a video by a conference called Compose Conference. Their conference is about functional programming, so stuff like Haskell. They have a video on bidirectional type checking, and that's the type checking system that I use in my Lucent compiler. The details of what bidirectional means are covered in there as well, but the first section of that video, like the first 20 minutes or so, they basically give an introductory guide to type theory in general. So you can maybe like skip the last 40 minutes and just listen to the first 20 minutes, and you'll get a really good idea of getting started with type theory and type checking. Now finally, my favorite book, I guess, is the guide to the Rust development. So Rust is the name of the Rust compiler, and they have written a really, really good guide on how Rust works. And a number of parts of my compiler is influenced or inspired by them. So my incremental compilation model is pretty much stolen from them. Hope they don't mind. And they go into a lot of detail on how each stage of the compiler works, including its type checking, its trait resolution. So if you're interested ever in programming languages, or maybe even contributing to the Rust compiler, I would recommend go checking that out. That's all. If you want to see my project, it's on GitHub, github.com/techno-coder/Lucent, or you can discuss with me on Discord in the #Lucent channel. This Discord's for programming languages, so that's why I have a channel there. So if you're interested, just have a chat. I think that's all.
Got a question?
Yes.
No, you go.
Yep. I don't know if you mentioned it at the start, but what was behind creating Lucent? You got a particular purpose in that language that it's going to be used for?
Kernel development, operating system kernel development.
Kernel development.
I was very. Yeah. I was frustrated with writing my OS in Rust because you would change one line and suddenly your entire OS breaks because of some unrelated issue. So I was like, no, I'm done with this, and decided to make a programming language for it instead.
I'm going to say maybe used in something like the is that called Coreboot, right? Is it Coreboot?
Not
really that.
No. Yeah.
Okay.
So your Lucent, does it compile to machine code or to assembly instructions?
Machine code.
Oh wow.
Yeah.
And you do that as well, or is there a crate for that, or?
So there is a crate for x86 instructions called iced x86, and I use that. But there's no crate for ARM. But their instruction set's a lot simpler, so hopefully I don't need to do that.
Have you thought about like LLVM IR or something like that?
I am skipping LLVM because one, they are a massive build dependency, massive compile times as well. And I feel like there's a lot of features in there that I don't really want as well. And I need a lot of control over the final output of the binary, and I don't think LLVM just gives me that level of control. So that's why I'm not using it.
Yeah. So, and you've got it like your previous, before you rewrite.
Yeah.
It was compiling, and was it running?
Yes. I used the hacks, so just like a shim for Mac OS. But theoretically, it was going to work for Linux and Windows as well.
Could you boot it? Would it boot?
So that time it was compiling to an executable.
Okay, yeah.
Yeah.
Okay, cool.
Yes.
At one point, like WebAssembly.
And what?
WebAssembly.
Yeah, I was planning to compile to WebAssembly as well, but I kind of scrapped that just because it's in the future.
Talking about opening processes in Rust, can you look at Redux?
Yes, I did look at Redux a little bit, although the code base was a little bit hard for me to understand. So what I did, I followed Phil Ops' tutorial on making your own operating system in Rust, and his tutorials are really good. So if anyone wants to write an operating system in Rust, I would recommend that.
Oh, yeah. I mean, going on that, have you looked at TOC OS?
Is that the
That's the
language operating system?
no, it's a real-time.
Oh right,
operating
yeah.
system.
I've looked at that. I think it's really cool.
What
Okay.
language is it talking about?
No, I don't think so. I think they want to do the same as what FreeRTOS is, but for Rust. That FreeRTOS is a real-time operating system and made for embedded systems.
Cool. So that's it. Yep. Then thanks for listening and have a great day.